Big story has been done out in Washington and Oregon, okay? Not a lot has been done up in Montana, even though the lake has been known by geologists since before 1910. The first article published was in 1910. Understanding the lake history, really draining and filling of the lake, is just beginning. There's a lot of unknowns. Optical dating, optically stimulated luminescence dating, that's how we get ages from these sediments. And I'll talk a little bit about that because we don't have any fossils, we don't have any charcoal, we don't have any volcanic ashes, other things that give us geologic dates. So I'll introduce that to you so you can tell your grandmother what it means. Correlations of lake sediments. So what's happening in the lake, what's happening down in Washington has been highly speculative. And in a nutshell from my work, the lake sediments seem to span an age from about 21,000 years to about right around 14,000 years, which is the timing of the last glaciation. This is what we're talking about. Glacial Lake Missoula is due to glacial ice coming down into Lake Pend Oreille. Lake Pend Oreille, the reason that lake is there, it was scooped out, it was filled up by a glacier, okay? And that, if you dam the Clark Fork River right there, somebody did a back of the envelope calculation, you dam the Clark Fork River, it'd take about 60 years to reform Glacial Lake Missoula. So all that water coming down out of the flathead down to the Clark Fork would make a lake. But there's also another lake, Glacial Lake Columbia, that was dammed by the Okanagan lobe. It's coming out of Okanagan Valley of Canada, dammed a lake here. But then there are this light blue, if you just look at Google Earth, you can see these channels that cut through Washington, and that's known as the channeled scabland. Super dramatic topography once you step back enough to see it. Now, when the lake failed, it drained all the way through here, flowed all the way up the Willamette Valley. Okay, so Corvallis was underwater. Portland was, the low points were underwater, and also the water went out into the ocean, and we can find deposits of these Glacial Lake Missoula floods all the way up near Vancouver, BC. Let's look at a topography right here, the Grand Coulee of the Columbia River. So this is a dry falls cataract. This stuff was recognized back in the 30s, the 20s by J. Harlan Bretz, published in the 50s, 60s, 70s, all the way up until this year. Here's this piddly little stream known as the Columbia River coming through this valley. Okay, here's the current location of the Grand Coulee, which has now been dammed for making electricity. But look at all these valleys, and these are known as cataracts. This is dry falls. There was water. The best explanation for this topography over this entire area, water spilled down the Columbia River, forming a cascading waterfall, and this is a plunge pool. These are plunge pools from these big floods that came out of Glacial Lake Missoula. This big valley is way too large to have what we now know as the Columbia River. Could have never carved this valley through hard basalt. This hard basaltic rock, volcanic rock, has all been sculpted by, these are channels from the big floods. Okay, so this is the topography you see in Washington. The water came, most of the water came from Glacial Lake Missoula. Okay, what else do we see? Here on the Columbia River Gorge, a field trip I was on back in the 1995, you notice this layering to these gravels. This is a big gravel pit. This is a gravel pit. I love gravel pits. Because this layering is at an angle. It's not horizontal. We call it cross bedding. And the analogy is if you walk down a sandy stream or a gravelly stream, you'll see these bars that progress downstream. Here the scale here is only 10 feet, 3 meters. And these crossbeds formed by a big bar moving downstream, sediments being transported from left to right and cascading and filling in this hole at the bottom. And that's what these things are, but they're just immense. You can get quantitative about it and estimate how much water would have had to flow through these areas, what kind of discharge, how much water was flowing, and it's a lot. I'll talk more about that. Okay, that's channel scale lengths. Let's talk about the chronology, timing of this stuff. The best paper, Benito and O'Connor, these two geologists. Jim O'Connor was here in Butte just this last fall. We went on a field trip together, still working on this stuff, back in 2003. They worked in the Columbia River Gorge, and the timing of the floods is constrained mostly by dating of deposits that are overridden by these big flood deposits. So you got a burned tree that got buried by one of these sandbars. And so, but they have a few dates from within, and they concluded it was somewhere between 23 and 13,000 years ago. Okay? But there was one big flood, 10 to 17 million cubic meters per second. And I'll put that into context here in a little minute. But greater than 25 floods of greater than 1 million cubic meters per second. Okay? So there's multiple times. But it makes sense. If the glacier comes down and dams the Clark Fork River, for whatever reason that dam fails, you drain the lake, what's going to happen? That glacier is going to advance and seal up the spigot again, seal up the dam. And so it would happen repeatedly. But in general, the floods got smaller over time. Okay, now we're going to go to Montana. This is a map I made years ago on Glacial Lake Missoula. And what I'm showing with the darker colors is where the lake would be if it was only 200 meters deep. This is all meters. Apologize about that. And as we understand, it got up to about 1,265, 1,280 meters, which is about 4,200 feet elevation. So you can see way up here, Butte's right here. Okay? Go down the Deer Lodge Valley, you go down to Gold Creek and Drummond, you start getting into what was the upper end, one of the little fingers of Glacial Lake Missoula. Bitterroot Valley, pretty shallow in here. It was only flooded if it was above 1,100 meters, whereas down here, if it was a relatively shallow lake, all of this would have been flooded in the lower part. So it's a complex reservoir. You have to think of it as a reservoir. This is the evidence for it. If you go to the Mission Valley, this is the Flathead River downstream from Kerr Dam near Sloan Bridge. These are glacial lake silts. Has anybody here floated the Clark Fork, the Flathead River? Been on the Flathead River downstream of the Kerr Dam. It's a popular place to go. I've never done it. Okay, anybody fished Flathead? Maybe? Yes. You guys are a bunch of Clark Fork River people. Anyway, this is a pretty popular stretch. I'd like to go do that sometime. Anyway, that whole embankment is silt, mostly fine-grained glacial ground-up rocks, and there's gravels in there too, that filled in the lake. And it's like 400 feet thick in the Mission Valley. Here in Jocko, if you've taken Highway 93 from Missoula up to Polson, you drive by this outcrop in the Jocko, and there's the lake silts there, sitting on top of some older gravel. It's only about 40 feet thick here. Okay, because most of that water and sediment was coming out of the Flathead, filling up the Mission Valley. But these are the kind of things I'm looking at. I'm looking at these sediments all over. So how can we better understand the Glacial Lake Missoula question? Can we explain the scabland floods with known sources? You know, we've got this big tank of water in Glacial Lake Missoula. We've got also the Columbia Lake, and we've got water coming under the glacier. Does the flood evidence in the scablands match what the Glacial Lake Missoula Basin? I'm going to be working on this until I retire, not more than 8 years from now. And I don't think I'm going to be done with answering these questions in the next 8 years. It's kind of a big problem. Okay. Ice dam failure. So you dam up, you advance an ice down, you back up a river. This happens all the time. There's ice lakes. There was one in the Highlands that spilled out towards Whitehall. Big flood deposits there. It happens in Alaska right now. It happens in Greenland. So this is not an uncommon sort of thing. So modern ice dam lakes, we can look at those things and try to understand how this process works. So you put ice in a river, you dam it up. As that lake fills, you're increasing the hydrostatic pressure. You go down to the bottom of the swimming pool, you go down to 200 feet depth diving, the pressures are pretty high. And that will actually break apart the ice if it gets high enough. There's also, you might get some subglacial tunnels developing, wet water at the bottom of the glacier. You might, with that pressure, you essentially hydrofrack, just like we do out the Bakken, just like we do in oil and gas. You have such high water pressures, you can actually break apart the ice. Or, and also that ice will tend to float a little bit. If you've got, we think the glacier was about 2,500 feet thick. And we know the water down at Plains, Montana, or Trout Creek was at least 2,000 feet deep. That's a deep lake. That at some point that glacier will lift up off the bed and you flow water out from underneath it. Anyway, there's a lot of things about thinking about how this actually forms, but the dam reforms at the tail end or after the flood is that glacier is still moving down from Canada. So this guy, Steve, at University of Wisconsin, put together this little graphic. Here's the Montana-Idaho border. The town of Heron, Montana is right here. Noxon is about right there. And Sandpoint, Idaho is here. This is Coeur d'Alene Lake. I'm sorry, Pend Oreille. Pend Oreille Lake. Okay? That's the glacier coming down from Canada that scooped out that lake basin. The idea is you start fracturing this ice, and that those fractures propagate down here, and eventually if you have a fracture going through, you're going to blow that ice dam right out quickly. The idea is the best guesses are the lake will drain in about 3 to 4 days. So how big are these floods? Now, kind of I apologize, I won't, whatever. Okay, discharge in millions of cubic meters per second. I don't even have a feeling for what that is. But here's 1 million cubic meters per second is that tick mark, okay? 10 million cubic meters per second is that tick mark. 100,000, 10,000 cubic meters per second is down here. So if you look at the biggest floods recorded, the Amazon River, the 3 biggest floods that have been recorded have been on the Amazon. And they're on the order of 80,000 cubic meters per second. No, 700,000 cubic meters per second. Okay? The Yangtze River in China, next big. So nothing in North America has ever been that big from a rainfall. The 1927 flood on the Mississippi River was 70,000 cubic meters per second. And that one dwarfed any other flood that we've seen in Mississippi. Okay, just to get a perspective. So 70,000 would be right about there. Ice jams and snow melt floods in Russia get up to about 200,000 cubic meters per second. Okay. Okay, now we look into the geologic record. Subglacial volcanic eruptions in Iceland. Iceland has ice caps, volcanoes go off underneath them, melts a lot of water, and you can get about 1 million cubic meters per second. There was another volcanic flow here. I can't remember where Untitled is. Okay, landslide dam failures, and these are kind of historic. These are not, these are prehistoric. The Columbia River was dammed in the Columbia River Gorge by a landslide about 8,000 years ago, and they estimate that flood was about 200,000 cubic meters per second. These are big floods, okay? And Lake Bonneville, a lake basin overview. This happened about 13,000 years ago. So Great Salt Lake filled up to its brim during the last glacial time, overtopped its divide, and cut a canyon, and came down the Snake River, ripped the guts out of the middle of the Snake River. That was on the order of a little over 1 million cubic meters per second. Lake Missoula, 17 million cubic meters per second. Okay, it's only topped by another similar landslide flood or ice dam flood in Siberia that was on the order of 18 million cubic meters per second. The kicker is Missoula happened multiple times. Everything else was a one-shot deal. So Lake Missoula worldwide is the failing of it is the biggest set of floods we have any idea of in the geologic past. One little other tidbit of information, 17 million cubic meters per second. That's the big flood from Missoula. That is far more than if you combine the stream flow from all the rivers in the world right now, you know, Amazon, the Mississippi, everywhere. This flood dwarfs the flow of all the rivers in the world right now. So it's really, truly immense, and it's really comparable to what happened on Mars billions of years ago. Okay. This is big. So what I'm going to do, we're right here in Butte. There's the pit. Flint Creek Range had glaciers in it. Go up the freeway, and you start hitting the lake right around Gold Creek. We're going to do a little flying tour to see some of this stuff. And thanks to Google Earth, we can do it right now. So I'm going to talk about this as we fly around. Okay, so this is kind of perspective view. And we're going to visit all these different sites and look at some of the geologic features that I've been working on. The first place to go is the town of Missoula. Because in the city of Missoula, you can see the shoreline so incredibly well on Sentinel and Mount Jumbo. So this is the high lake at about 4,200 feet. I'm going to take the lake away, and you can see the shorelines. If you're down in the Missoula Valley, those are the shorelines of Glacial Lake Missoula, okay? And so when that lake drained, it drained down the I-90 towards what's known as 9 Mile. 9 Mile's a creek coming in from the north, and the classic 9 Mile section of silts is right here on the freeway. You drive it every time you go between Alberton and Missoula. And we'll look at more of that section. Now I'm going to turn around and fly down the Clark Fork River through the Alberton Gorge. Okay? Alberton Gorge, a lot of sediment is stripped off the hillsides on the outside of the bends. That is erosion from the draining of the lake. And then you go on this side, there's that stripped bedrock here. And this is the town of Sear, another great place to go boating. This hill is all gravel. As water was coming out here, there was a big eddy bar, and this 300-foot high hill is of gravel that was ripped out of Alberton Gorge. And then down to Tarkio, again, stripped hillsides on the outside of bends, Tarkio is another fishing access site. Right here, this big bar is gravel. The Tarkio bar that is evidence of these big, high energy drainage events. On a field trip, I commonly go to this site here, and you can see those foresets of a bed form that's been stripped off now, part of that bar. Then as you go down to Quartz, these are little towns that you may not have heard of, but you've driven through them. There's silt covering that bar. There's this fine-grained silt deposit on top of the bar, clearly from a younger lake. That silt would be completely ripped out in these big floods. So we're seeing big floods, little floods. There's a bunch of gravel behind this hill, and we see flow splitting around that bedrock knob, depositing a wedge of gravel on the backside, because I was mapping the geology here. Here's the town of St. Regis. The river's taking a right, the freeway's going to the left. There's this beautiful little channel cut in bedrock there. I believe this is from a flood channel. That there isn't any stream in it now from the drainage. And then you go down the canyon heading for Paradise and Plains, and it gets really narrow. And there's huge imbricated boulders as big as these tables sitting next to each other that are from the flood deposit, basically right at river level. The river hasn't cut down since 15,000 years ago. Wherever the valley opens up a little bit, you get another gravel bar. There's a gravel pit on a big gravel bar, but it's covered again with these silt deposits, these really fine-grained stuff like flour that is a more recent evidence of more recent lake fillings and drains. Clark Fork River comes into the flathead near the town of Paradise. This is where the big water was. The big water was up the Flathead River, and you've got these little eddy bars in here. So this is how deep the lake was. When that dam fell, you end up with a big sloping water surface, and water's rushing through here. And most of the water is coming out of the Flathead and headed down towards Plains and Monterey. So this is where J.T. Pardee in 1910s, and he published in 42, looked at how deep the lake was, how steep the slope was, and calculated a velocity through here, just from good old slide rule math. And he was right. He predicted it correctly. Going up Highway 200 towards Dixon, Montana, here's the Burgess Ranch, an old family ranch here with a big lake. That lake is scooped out by high energy flow, cut into bedrock, and there's another gravel bar tucked up in the valley. There was so much water coming down the Flathead, you couldn't build these big bars like Tarkio. You just had little gravel patches up the valleys. Going up to Perma, here's a side drainage. I believe it's Camas Prairie Creek, but I'm not sure. But this is Camas Prairie, a little ranching area. And this is where J.T. Pardee published in 1942 the classic ripples. Do you see that pattern of ribs? Those are like little ripples that are, 40 feet high from big water flowing through these passes from the Flathead Valley. Because look at the water was very deep in the Mission Valley. The glacier was up in the Flathead Valley. Folsom Moraine was the end of the glacier. And so, again, big water was up here, and when it drained down the Flathead, but it also spilled over into the Camas Prairie, forming those classic ripples. Again, another look coming through these little passes here, where you can see a whole pattern. So there's another set over here. Now even before, and also what was happening, water wants to take the shortest route downhill. The shortest route downhill was through Rainbow Lake. It's called Dog Lake by the Salish Kootenai tribe. It's on the reservation. But when it initially failed, the highest velocity water came through here, only when it was very deep, and scooped this lake basin right out of bedrock. It just, the high flows pulled bedrock right off the bottom, because it was getting into the plains area. We're buffering. Okay. Now, so all the water now, you had it coming in from St. Regis, from Bitterroot Valley, from the Flathead, and it was headed down towards the ice dam. So this is where the ice dam broke. If you take this thing away, you're draining the lake. And now see, I just put the edge right there on the state line, because it was probably various places. This is a very deep lake. You know, they did submarine testing back in World War II there, because it's about 1,000 feet deep, the lake. The sediments go down below sea level. I worked with a graduate student out here. We still have a map that we want to finish, and we mapped this area, and there's this anomalous hill right here, and there's a big pile of gravel here. I think that is a terminal moraine of that glacier. It had actually made its way up here at one of the times. Okay. So I assume people have been around Montana. You may have seen some of these areas. But this is kind of an overview. Now we're going to go back up to the Mission Valley again, where most of the water came from. And we've got one more stop to make. Let's head up towards Butte. So, the Clark Fork River, as you know, comes into Missoula through this canyon, okay? And the Blackfoot River comes in. We've got the Blackfoot up here and the Clark Fork up here. I've been working up here, but most recently I've been working a lot on this little spot, Lake Missoula beds, where I call it a Garden Gulch. You've driven the freeway to sometime between 1890 and now, there's been a cut through this old bend in the river. The railroad straightened out that bend and cut into Lake Missoula sediments right there. I'm going to talk more about that as we go. That's kind of an overview of the basin. Okay. So, slow down a little bit. 9 Mile. Go down the freeway. You look, next time you do this, look to the left or right, especially if you're not driving. There's really rhythmic sediments in that cut, okay? And those have been interpreted as, and I haven't worked this in great detail, but up to 34 lake level fluctuations in the lake. That you've got repetitive filling and maybe not entirely draining, but lowering, okay? Water going in and out of the basin, and that's how they've been interpreted. Garden Gulch section, I was just talking about coming up towards Butte. Next time you see it, you can drive right by that. I always slow down and look at it every time. You can see my cuts. I've been trenching into that thing since 2009. This is the cut here. And if you just stand right on the freeway and take a panoramic view, this is what you see. Again, you see fine-grained sediments that are well layered, that has some sort of record of draining, lowering and raising of lake level. This is what I did. This is what geologists do. You spend years making mistakes and then going back and fixing them and ending up with a measured section of those silt deposits. There's 9 meters or 10 meters, so about 30 feet of section. It took me 3 years to actually do this because I counted every little lamina in there. What you see, what these logs are, is the detail. Coarse grain stuff like gravel's over here. The super fine grained clay is on the left. So anything that bumps out is coarser, and then it, just a little coarser, then it fines up, and then boom, you got a coarser, oops, wrong button, coarser, fining up, coarser, fining up. In a nutshell, and at these levels, I see evidence it was exposed to the sunlight, okay? It was exposed to the cold weather of the glacial period. So each one of these cycles, and I counted 11 exposure surfaces, 12 cycles of filling and then lowering, exposing the lake bottom to the weather, and then filling again. So what does this all mean? I want to show you what I actually look at. So down at the very bottom, you got sand and gravel. Basal sand and gravel. Looks like stream deposits. It's the old Clark Fork River. And then right there is a laminated silt deposit. That's the first filling of Glacial Lake Missoula at this area. Rhythmically laminated silt. It fluctuates winter to summer, and you get coarser grain stuff in the summer because things melt and water flows. You get finer grain stuff in the winter because the lake surface probably freezes, the water freezes, and you just have clay settling out of the lake. So I looked at this whole thing. And what I did is I hammered these tubes, metal tubes, in to collect sediment for optical dating. So I did 31 days. Okay. Right here at one of these exposure surfaces, I call them exposure surfaces, what you see are laminated silt deposits, but they're getting disrupted. Okay? And then there's sand and gravel in these kind of downward tapering wedges. And I'll give a little interpretation. You've got nice, good lake deposits all through here, but they've been disrupted. Little fractures and faults and stuff going on. I interpreted that as an exposure surface. That this is due to permafrost action. Frozen ground, like we used to get in Butte. Haven't had that for 20 years, 15 years. And then the lake comes back, and you get nice laminated silt again. There's one of my tubes that I broke. I couldn't get that out of there. So I got a date right there. I hammered this tube in to try to date the last time that sand had seen the sunlight. And, you know, not to belabor the point, but they change. Here's another exposure surface there, there's one there, there's one there, there's one there. And I sampled a whole bunch of tubes. Okay, I'll talk a little more about that. But paraglacially modified. Para, close to glacier. Okay? So it's frozen ground. Think Alaska. Think northern Canada. Or central Canada at least. With downward tapering wedges of sand and gravel. What do those mean? This is the kind of thing where you get downward tapering wedges. You get, when it really get a cold snap, back in glacial time, or up in Alaska, the grounds will crack. Okay? They freeze so quickly, they crack. And they open up. And you get sediment pouring in that open crack. And then that happens year after year, you get cracks that are filled with sediment. And that's what we were seeing in those previous slides. And if you're looking down from the air, you get this glacial cracking. Okay, that's the interpretation. Okay, so why is this Garden Gulch important? This is way the heck up here near Drummond. So if you wildly vertically exaggerated a cross-section from Drummond to the Idaho-Montana border, this is how deep the lake was down here. The lake was much shallower in this area. So any sediments that you see at Garden Gulch must indicate the lake was at least this deep. A lot of folks have worked at the 9 mile section I showed you before. That's way the heck down here in the low country. That the lake might have only been this deep to record the lake level fluctuations at that location. Okay? At that location, the lake might have only had 10% of the total water that it would have had at the top. Up here, it was at least 70% of the total. I'm curious, when did the big floods happen? And you do that by looking at sediments that had to have been deposited in the deep lake. Okay, so how can we better understand? There were many big and early floods, and then later floods were smaller. How does this work? You need optically stimulated luminescence dating. Most of us geologists love carbon-14, burned logs, because you get a nice good date back to about 50,000 years. We like fossils. We like all these other volcanic tephra. We can't find any of that in the sediment. So we got to use this technique. And it measures the time since a grain of sediment was exposed to the sunlight. So crystal structures are imperfect. Everything's imperfect. They have little electron traps in there, and if you get natural ionizing radiation, uranium, thorium, potassium, everything's radioactive, it excites electrons to fill those traps. However, if you expose that crystal to sunlight, it excites it and they luminesce. You actually see a luminescence. This is how luminescence works. The same thing happens. Has anybody had a radiation badge on or seen one? You know, if you go to the dentist or when I go to the doctor, I have to get x-rays for my dislocated shoulder, that the technicians have to wear these radiation badges. They sample how much ionizing radiation they're being exposed to. It works exactly the same way. They put a mineral in there in the dark, and it gets excited by that radiation, and then they bring it to the lab and they expose it to a wavelength of light and look at how much luminescence is coming off of it. And they can measure how much radiation that badge had seen. We do the same thing with minerals. Salt works, quartz, feldspar, most minerals work, but we use quartz and feldspar. So what do? You have to collect quartz or feldspar in the dark. You pound a tube in, you cap it off, and you prepare the samples in the darkroom. Okay? Then you expose the grains to a specific wavelength of light, and you measure how much luminescence. Is it X or is it Y? Is it 1,000 or is it 10,000? Who cares about the units? And then you also have to measure how much radiation is coming into it. So you take a sample of the sediment and you measure for uranium, potassium, for all the radioactive minerals that are out there. And the age is simply a ratio of the amount of luminescence to the radioactivity of the sediment. And that, I was in Denmark for 4 months and worked on 40 samples, 40 to 60 hours a week to do this.
A day.
It's tedious. But it's nice and dark there. So this gal, Michelle Hansen, for her PhD, got a date from the bottom of the 9-mile section by the same technique. 15,000 years, plus or minus 600 years. Good. We also know, this is pointing just at the top of the section, that there's no way the lake was around when Glacier Peak puffed off a big explosion, 13,000 to around 13.5. So we know the lake was gone by then. So she concludes this sediment had raising and lowering between 15,000 and 13.5. Okay, that's way down here, 9 mile. Let's look up in the deep part of the lake. I got a bunch of data. And this is exactly the same kind of data I gave at a big professional conference, so I apologize for all the numbers. Down at the bottom, I'm getting 23,000. There's a lot of error bars here. Error bars. We don't know everything. Ignore these two. 20,000 years. Okay, 20, 21, 22. These can be explained. This is a separate issue of a slump within the lake. Up at the top of the section, 20,000, 21,000, 18, 17,000, okay? These are a lot older than what Michelle found down at 9 Mile. Now, the lake was gone by the time these three dates, sediments were laid down, and that makes perfect sense. 12,000, 11,000, 10,000, okay? So, I don't have any dates from the very upper part of the section, but I'll summarize here. Ages, 15, 20,000, 25,000, 30,000. Those are all the dates I showed you. And then the ones right at the top. So this is all around 17, 20,000 years ago. So Garden Gulch appears to be old. The lake filled to greater than 65% of its capacity at least 11 times from 21,000 to something around 17. More may have occurred in here, but the lake was gone by 13.5, 14.2. Okay, I'm actually wrapping up. So this whole system, we've been working, I just worked on this one little spot here, Michelle worked down here. I've got other samples coming from various points in the lake that are still in process. Down in the Scablands, they think flood deposits record 25 to 100 lake floods, okay? Big floods were early, around 19,000 years. Later floods were smaller. Lake Missoula deposits up at Garden Gulch, I'm saying 21 to 17,000. So that's definitely similar to what they're saying down there. So the full drainages may explain the big floods. But the 9 Mile section, we're talking 15,000, 14.2, somewhere in here. These are shallower lake stands that may have been some of the smaller floods. Not important to this crowd, but folks have been arguing for 30 years that everything going on at 9 Mile explains everything there. And I think there's no way that works. Okay. For more information, there is the Ice Age Floods Institute, which is a nonprofit group. There's 11 chapters, including the Missoula chapter, Sandpoint, blah, 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 all the way down to Portland and Seattle, that have additional meetings, additional talks, additional information. If you're on the web, they've got a website, iafi.org. I've led trips for these folks, and I've given talks for at their meetings in the past. Unfortunately, they meet like Wednesdays down in Missoula, and I have a regular job, so making it to a 4 p.m. meeting on a Wednesday down in Missoula, even making it any meeting in the middle of the week down in Missoula is very few and far between. But I know they've brought in other speakers that have talked about all sorts of stuff having to do this at the Natural History Museum in Missoula. There's a lot more information out there, and I really wanted to end with that because I'm just an academic. Okay, thanks.